I'm a data scientist, also a mathematician here. I've been working in the area of cybersecurity for probably 8 to 10 years now, applying mathematics to data found in the cyber domain. And so what I'll talk about today, I'll start with kind of setting the big picture at the very beginning here. What is cyber data and how it aligns to the cyber kill chain and some of the big challenges. And then I'll spend the majority of the time talking about opportunities for mathematicians and where we've, mostly the work that we've done here on addressing some of these opportunities, mathematical models of cyber data, some anomaly detection, and at the end, a little bit of an application of math together with machine learning. So let's dive right in. So first thing, setting the stage, Internet of Things is everywhere we look now. This slide is a little bit old, so it's even more prominent. And so the importance of studying cyber data and analyzing it is
Emily, I think you accidentally muted yourself there. So.
Shoot. Okay. Where did
like
you hear
5
anything?
seconds, 10 seconds back.
Oh, okay.
Yeah.
All right. So I will try to not do that. All right. So thank you for letting me know. Just the point here being that cyber data is everywhere, interconnected devices are everywhere, and so it's just even more important for us to be able to analyze and understand what these systems are doing. Okay, there we go. So the sea of data, there's all kinds of data that we collect from cyber systems or that can be collected by the people that run these enterprise cyber systems. So DNS request is one where we're, human asks for example.com and we need to translate that to an IP address. And so how do we do that translation? We ask a domain name system server, what's the IP address that I should go to? And so that's those are DNS requests. Flow is this flow of information whenever you go to a website, whenever you authenticate, anything that goes across the network, information is being collected or sent rather. And so the roll-ups of that information, just the source and destination, the number of packets, number of bytes, the timing, all that is collected to aid cyber defenders within a network. Authentication is another one. Whenever you sign in SSH to a computer, all that authentication is being logged, again, for forensic analysis. Firewall, anything going in and out of a network hits a firewall and is inspected, and those logs are collected. Signature-based alerts. These are tools that people deploy, so rules that we know the adversaries use. An adversary might use a particular technique, and if we know how to kind of template that technique, what it looks like at a high level, we can set an alert rule that says, if you see this kind of behavior, let me know, so that we can flag that and hopefully stop it before it happens. So, and these are techniques that we already know about, we can flag, and those alerts then can be used as data. And then lastly,
okay.
Yes. Sorry, was there a question? No, maybe just a errant microphone. Lastly, at least for this slide, is process logs. So this is capturing whenever a host kicks off any kind of process, a command line, opening a program, clicking sometimes. So lots of these different processes are logged. Again, so this is this big sea of data that we can use to understand a network. So how does this align with a cyber kill chain? So on the left picture here, I've annotated this cyber kill chain from recon, weaponization, delivery, exploitation, installation, command and control, and actions on objectives, with some icons from the last slide of what kinds of data might be seen at any of these steps. So it lays out the steps that an adversary goes through to compromise the system, and it helps us organize how we think about detection. Of course, we want to detect earlier in the cyber kill chain rather than later. Weaponization is something that happens remotely. It's on the adversary's system, and so that's something that we don't have any insight into. But the reconnaissance, the delivery of an exploit, the actual exploitation, running the code, installing something, calls out to command and control, and then actions that the adversary does on that target system. Those are all things that a cyber defender could see in their own network. So how do we protect? Well, we have to inspect the data. So all the data that I mentioned on the sea of cyber data, the cyber defenders for a network can inspect that to try to discover known patterns of bad behavior and unknown anomalies. They can also build in resilience so that the network is up even if there might be some amount of adversarial activity. The folks can still do their work. But for this talk, we'll be talking about inspecting the data to understand different kinds of patterns. So some of the big challenges, one is that cyber systems don't have laws of physics type rules. So every rule that is sent down in a cyber system is basically a standard that could be broken. They can be broken by adversaries, certainly, but they can also be broken by people that just don't realize there's a rule. And so when you see rules being broken, it doesn't mean that necessarily something is bad. So that's a challenge. Additionally, adversaries are finding vulnerabilities and exploiting them much faster than defenders can identify them. If you think about it, the adversary only has to find one vulnerability and the defenders have to defend against all of them. And so it's just, it's a race against, fixing all the vulnerabilities, which are, continually get introduced by new software and things like that. So while signature-based are still necessary, threat hunting and anomaly detection are also quite helpful, but the caution is that an anomaly on one network could be perfectly normal on another. So if one network uses offsite backup and another one doesn't, well, transferring a bunch of data off of the network is going to be perfectly fine in the place that uses offsite backups, but pretty damaging if you're not using offsite backups, right? Why is somebody transferring so much data off of the network? And so it's hard, or it can be hard, to transfer rules or tools from one network to another. As again, all of these rules or standards can be changed depending on how you instantiate. So where do mathematicians fit? There's this notion of an OODA loop, which is not cyber specific, but in a lot of different areas, where you observed, you collect data, you orient yourself, you develop some sort of situational awareness, maybe you run analytics on the collected data, then you make a decision, what should we do based on the observations? Maybe you want to patch the network or segment it, add a honeypot, target some additional data collection, whatever, you make that decision, and then you act, you carry out those actions, and you continually do this loop. And it's not like you do the loop, and if you're in orient, you're not in observe. You're always in every bucket because this data is coming so quickly. So you're constantly observing, orienting, deciding, and acting. Mathematicians, I think, fit best in the orient and decide buckets in this developing situational awareness from data, and sometimes helping make those decisions, maybe game theory and other kinds of tools to figure out what to do and how to keep our networks healthy and running. So that's the big picture up front on the cyber landscape from my perspective and where mathematicians can fit in. And so what I'm going to focus on next, and for the rest of the talk, is what my team has been doing on applying some mathematical methods to study cyber data and what we've found. And hopefully this provides some ideas of where else mathematicians can help with analyzing this kind of data. So I'm going to talk about three kinds of mathematical models in particular. So first is graphs. Graphs model pairwise relationships in data where edges connect pairs of vertices. So in a cyber use case, we have source and destination IP and network traffic. So your vertices are your IP addresses and your edges connect pairs of IPs when one is the source and the other is a destination in a single log event. Another kind of example would be malware similarity, where your vertices are malware binaries, and then you connect to malwares if there's some notion of similarity, however you end up defining that in your particular application. So that's graphs. Hypergraphs, generalized graphs in some way, to model multi-way relationships in data. So here we still have vertices or objects, but now in a hypergraph we have hyperedges that associate groups of vertices. So instead of pairs being related, we have some sort of group. So a particular example would be IP versus domain in DNS. So you have a bunch of IP addresses that might all resolve to the same domain. Those aren't necessarily pairwise relationships. They are relationships or a property of a bunch of IPs that have, one domain in common. So this picture at the bottom shows a hypergraph visualization of so the IPs are vertices and the domains are hyperedges. You could also look at user versus host in authentication logs. So a group of users that authenticate to the same host would be a hyperedge, or source IP versus destination port in network traffic. So all of the source IPs that use the same destination port, they're doing similar things because they're using the same port. That would be another example of hypergraph. And lastly, for my work would be topological objects. So what this topological objects, I'm going to get into more detail a little bit later, but they provide a kind of an additional perspective on multi-way relationships. They capture some amount of shape signature for high-dimensional data. And in the cyber use case, we construct these from cyber hypergraphs, and we derive them from point clouds using some featureization. And I'll get into details of that later. Oops. All right, so the methods then that I'll talk briefly about each one of these, network science, hypernetwork science, topology, persistent homology, and zigzag persistence. So we'll walk through these in a logical order, starting with network science. So I've already kind of described what a graph is, right? It's a bunch of vertices connected by pairwise edges. Network science is a method to study the structure of graphs from real data. And you can do a lot of different things in this domain. So degree is one. So for every vertex, how many, if these are IPs, let's say, how many other IPs do they talk to? That's the degree of a vertex. And then you can look at the distribution of those degrees. How many vertices have degree 1? How many have degree 2, 3, 4, and so forth, and start to see a notion of structure of the graph. Walks in a graph is something that can also be really important. So if this may be in an authentication graph where you're looking at authentication from one computer to another. Long hops might be looking at lateral movement within a network, which is something that you would want to know about. So a walk or a path are interesting to identify and follow, and then diameter is the longest, shortest path in your network. So in this particular example, which is not a cyber example, it's a power grid actually, but the going from the tippy top to the very bottom is like the longest way you could walk or without repeating vertices and edges in this graph. Knowing the diameter can sometimes be important. Looking at the connected components, so how many components that are not, a connecting component being a place where every pair of vertices you can walk from one to the other by edges, and how many connected components you have could be of interest. Centrality, I'm not going to go over all of these. I'm going to say a little bit more about centrality, I think, later, but notions of when a vertex is central. You might define that in different ways depending on what you're looking for. And so finding important vertices or central vertices can be of interest. And there's just a lot of different ways that people have defined this. And then notions of triangles can be fairly useful in understanding the structure of graphs. And so clustering coefficient and triangle counting can be relevant. So finding triangles, identifying how many there are, how many are present at a single vertex, things like that. And then just a slew of more network science methods are pretty commonly applied. So network flow, I've already kind of described how this could be a graph, but I'll make it a little bit more concrete here. If you have one single flow record that's has a source IP and a destination IP, a source and a destination port, a time, start and end, some like wait metadata like packets and bytes, some other metadata like what is the protocol that we're using to communicate. All of that information can be boiled down into a single edge in a graph with some metadata on top of it. So here I've got an edge between the .13 IP address and the .1 IP address. Sometimes you might want to annotate these with port numbers as well. Typically, the source port isn't very informative, but the destination port is, so that's where we might see more information. And then you can append the metadata, the protocol, and the weights on that to make it a weighted graph. And in large networks, these graphs can start to get really big. This is a fairly small graph by graph theory standards. And it's only 2 minutes of flow from data that came out of Los Alamos lab probably a decade ago now, but it's a very nice data set if you want to kind of get your hands wet with cyber data. There's a lot of different kinds of data sitting there, not just flow. But in any case, just taking 2 minutes of that provides this graph, and notice that there's a number of different connected components here. So what we did in one of our projects was apply something called spectral graph theory to study these cyber graphs. And so as a brief reminder on what is spectral graph theory, it comes from eigenvectors and eigenvalues, and it comes from linear algebra. So if I have a matrix, I haven't told you what that matrix is yet, but if I have a matrix and I multiply it by a vector, and that equals a constant times that vector, then that vector is called the eigenvector, and that constant is called an eigenvalue. And understanding eigenvectors and eigenvalues tells you something about the structure of that graph, or it can. And so spectral graph theory is applying this notion to graphs that come out of, matrices that come from graphs. So if you take a graph, you make a matrix, and you compute its eigenvalues, those eigenvalues can tell you something about the structure of the graph. It can tell you about connectivity, about path lengths, about chromatic numbers, independence numbers, spanning trees, tons and tons of stuff. And there's multiple kinds of matrices that you can create from these graphs. So one is the adjacency matrix. Here we have a 1 if there's an edge between vertex I on the row and vertex J on the column. So here between in the 1, 2 spot, there's a 1, but not in the 1, 3 or 1, 4 spot because there's not an edge between 1, 3 and 1, 4. And the eigenvalues tell you some things about the graph in the case of the adjacency matrix. There's also something called the combinatorial Laplacian. This matrix, you put the degree along the diagonal, and then you take the negative of the adjacency matrix on the off diagonal. So vertex 2 has degree 3, so that's here, and then it has its connections as negative as it had in the adjacency matrix. The combinatorial Laplacian is always positive, and the 0, there's always a 0 eigenvalue because the row sums are always 0, and the number of 0 eigenvalues tells you how many connected components you have in the graph. And the lower eigenvalues tell you things about the connectivity structure. The higher eigenvalues tell you things about the degree structure. Normalized Laplacian is very similar. It's a rescaling of the combinatorial Laplacian. So notice I've got 1s all along the diagonal, and I've got still negatives on the off diagonal in the same places as I had -1s before, but they're just rescaled so that I have normalized everything out. The maximum eigenvalue you'll get in this case is 2, and that's if your graph is bipartite. And then there's other properties of the eigenvalues in between. So why am I going to tell you all these things about spectral graph theory? You'll find out in just a couple of slides. I mentioned earlier that people want to measure vertex importance or centrality, so just a couple of examples of those that I glossed over before. One is closeness, so measuring the average distance to other vertices. So how close am I to everybody else? That's a notion of centrality. Or maybe I want to know how frequently I am as a vertex on a bunch of shortest paths. Am I a bottleneck? That's another way of being central, and those don't necessarily correlate. PageRank is related to the stationary distribution of a random walk. So if I'm randomly walking along the graph, how often do I land on myself? And then CAT centrality is related to reachability as well, farther vertices being more penalized. But another one is called the Laplacian centrality, and this notes the change in the spectrum from removing a vertex. So I just told you about the spectrum, so let's talk about the combinatorial Laplacian, for example. If I grab all of the eigenvalues, so lambda I are all of the different eigenvalues, I sum up the squares of the eigenvalues, I get a particular value, the Laplacian energy of the graph. If I then remove a single vertex and recompute the Laplacian energy of the graph with that removed, that's this term here, and I look at how much I perturb that Laplacian energy by removing that vertex, that's a notion of centrality in the graph. How much does removing my vertex change the structure that we can calculate using the spectrum? And so all of these plots are showing, what different kinds of vertices are highlighted by different centrality measures. And you can see that there's quite a difference. And so it really depends on what you're looking for as to what you want to calculate. There's just a slew of these centralities. And so my group came up with one more called the directional Laplacian centrality. And so what we thought was in the Laplacian centrality, you remove an entire vertex. This does a lot of damage to a graph, or it can. And in the case of a cyber system, it might not make sense for a whole computer to go down, but maybe it gets slowed down, right? It gets bogged down a little bit. And so rather than removing the vertex wholesale, instead, we want to think about making an infinitesimal change to the graph structure. So sort of just fade a vertex in and out just a little bit and see how that changes the eigenvalues. And so what this leads to is the notion of the derivative of an eigenvalue in the direction of a vertex. I have a paper up at the top if you want to look at the details of how we derive this and how we compute it. That's not what I'm going to talk about today because I wanted to get through more than just the one example. But just to give you the sense of what we're doing is this derivative of an eigenvalue. And we can do this for any subset of the eigenvalues. You can do the same thing for the Laplacian energy. You can compute it for just a subset of the eigenvalues. It doesn't have to be all of them. And we note that the smallest eigenvalues and the largest eigenvalues tend to have more to do with the structure of the graph. The middle eigenvalues tend to be less well understood as to how they correlate to various graph structures. And so we came up with this K-DLC and K-bar DLC to look at the smallest eigenvalues and how those change when you fade a vertex in and out, and how the largest ones change when you fade a vertex in and out. And again, for comparison, these are the Laplacian centralities on the right and the DLCs on the left for the top 5 and bottom 5 eigenvalues. And again, you can see that they're highlighting different properties. So how did we apply this to cyber data? So we applied this to the LANL data. We picked one particular base graph, a snapshot from a small time window with around 2,000 vertices and 2,500 edges. And we injected some anomalies to measure then the perturbation of our DLC measures. So we injected stars. So this might be like a denial of service attack would look like a star, one node contacting a lot. And we also injected a clique, and maybe this is like lateral movement, sort of moving around a small subnetwork. So first we did this at low importance vertices. We computed all of the importance scores, the DLC scores for the base graph, and then we picked some of the low importance vertices to inject the anomalies at. And a lot of the vertices are low importance. And then we did a another experiment where we injected just the star of different sizes randomly throughout the network to see if we could also detect where that star was occurring. So I'll just show you briefly what those results looked like. So I'm going to explain these plots so you don't have to read all about them. What we are seeing here, each one of these 4 plots is for one of the DLC. So this is the largest 5 eigenvalues for the directional Laplacian centrality, largest 5 for, the star injection, the clique injection at the bottom. And here is the normalized directional Laplacian centrality. So this is the same thing, this derivative in the direction of a vertex for the normalized Laplacian, this is for the combinatorial Laplacian, and this is again star and clique. So on the x-axis of each one of these plots is the size of the injected star or clique, and on the y-axis is the percentile of the DLC computed for the root, the average of the leaves, or every vertex in the clique averaged. And so a couple of takeaways. The first takeaway is that you only have to inject a star of roughly 7.5% of the vertices to jump the importance value of the place where you did the injection up to basically the 99th percentile. So it's just the biggest thing. So that's 7.5% of the vertices is still pretty big compared to the degree of most of the vertices. But just to see that you don't have to go all the way up to the top to start to see these things. The second thing to point out is that even a really small injection increase the percentile of the anomaly score by an order of magnitude. So it goes from 10 to the -1 to 10 percentile with just a few edges added. So this is saying that it is somewhat sensitive. If you look at the percentile of the score and you look for jumps in the percentile of a score over time for a particular vertex, you can see small anomalies popping out. And then the last thing is that the K normalized directional Laplacian centrality doesn't seem to be sensitive to the injected star. So that's an interesting, observation. So that was targeted injecting the star and the clique at low importance vertices. Now what about if we inject at a random place? Can we still see if we inject randomly? And so what we did was we picked a random root and then random K% of vertices and wanted to test first detection. Does this increase the importance score of the root? And second, sensitivity. If I make the star bigger, does the increase in the importance score get even bigger? And so what we saw, what's highlighted here is that the directional Laplacian centrality does both detection and sensitivity. So it's definitely a change in the score and a bigger change the more we inject, whereas the normalized directional Laplacian centrality, we see a change in the score actually goes down and not up, but it doesn't, it's not sensitive to smaller or larger injection. So that's another interesting observation. So this was just one example of where we took this concept of spectral graph theory, pull it from math and apply it to cyber data and see where we can use it to identify anomalies, anomalous patterns within the graph. And so next, I'm going to move on to tell you about where how we can build hypergraphs from cyber data, and then how we've applied topology to study those hypergraphs. So reminder, for those of you that don't live and breathe these things like I do, again, hypergraphs provide this mathematical model of data focused on multi-way relationships. We've got vertices, which are our objects, could be IPs, could be users, could be malware, could be all sorts of things. And then we have groups of those vertices, which are hyperedges. Could be a port, could be a host, could be all sorts of things. And when we want to do this, we want to model these multi-way relationships. Again, just like in graph theory, where network science studies graphs that come from real data, hypernetwork science, we do very similar things to study hypergraphs that come from real data. Degrees, edge size, this is a new one. We don't care about the edge size distribution in a graph because every edge is size 2, but now in a hypergraph that becomes interesting. Walks, paths, diameters. I have a whole talk about hypernetwork science and where we've used it. Here, I'm not going to highlight any of these things, just to say that you can apply all of these kinds of tools in a hypergraph context in CyberData. What I want to tell you is how we build hypergraphs more specifically from CyberData in kind of a framework way. And I'll use this data from DARPA as an example. So this is called the Operationally Transparent CyberData. It's a large data set from a simulated network with around 500 hosts, has some days of benign data and some days that have red team behavior. And what's nice about this data set is it has like all of the data that I mentioned on the sea of CyberData all bundled into one data set. So we've got processes, we've got flows, we've got registry edits, modules, threads, all sorts of things, all bundled into one. This is a snapshot of some of the flow data, just to illustrate one way that we can build hypergraphs. So from tabular data, which this is, to create a hypergraph, you have to choose two things. One, hyperedge columns, and two, node columns. It doesn't have to be a single column. It can be a group of columns, as I've done here. My hyperedge columns are at destination IP and destination port, and my nodes are just one column in this particular case, but it could be a collection of columns. And we say that a vertex, so let's say .198 vertex, which is this bottom one here in the picture, it is contained in a hyperedge if there's a record that has that particular combination in the data. So the .198 source IP occurs twice in this little snapshot with two different IP port pairs. And so that means that that particular IP address vertex is going to be in two hyperedges. And in fact, it is. It's in this orange hyperedge and this blue hyperedge, representing the two different IP port pairs. And what we think about is hyperedges are like common behaviors. Every IP address, every source IP within one hyperedge are somehow doing the same thing. They're contacting the same IP for the same purpose, which is the same port. And what the hypergraph then does is looks at how these different behaviors interconnect and interrelate. So patterns of behavior become motifs in hypergraphs. What do we then do? Well, we apply topology to study these hypergraphs. In particular, what is topology? Well, topology is, I think of it as stretchy geometry. Two different shapes are considered the same if they can be continuously deformed into one another. This is all very abstract and not cyber at all, but it will become less abstract in a moment. So homology is a method that we use to count holes, or we kind of analyze what is the shape of my topological object. So these are three different topological objects, a bunch of vertices connected by edges, connected by triangular faces, and solid tetrahedra. And they have different structures, different shapes. Both of these have a hole that's enclosed by a cycle. This one has a void that's enclosed by a surface. This one has two different connected components. And all of those are properties of the shape of these objects. And homology is then the study or quantifying these holes. Homology is the foundation of something called topological data analysis, which I do a lot of, and is very useful to study real-world data. In the cyber context, we study homology of, these are called simplicial complexes, these collections of vertices connected by edges, connected by faces, connected by tetrahedra and higher dimensional structures. We study simplicial complexes derived from cyber hypergraphs in different ways. I'm not going to go into the details here because we have a paper that I'll point you to where we're discovering behavior patterns as topological structures in cyber hypergraphs. This is just sort of a illustration of how we take a hypergraph and we can create different topological objects, different simplicial complexes from the same hypergraph and study different shapes. And what we find in this paper, or we walk through, is how you could take a really messy hypergraph like this one that's coming from IP port and user information in the OptC data and identify small sub-patterns that are interesting. So in this particular case, this sub-pattern was calling out to command and control IP addresses that were taken over by adversaries and then called out to command and control networks. So another method that we use in topological data analysis is persistent homology. And this is applied not to hypergraphs, but to point clouds or metric spaces. Now, a point cloud will have trivial homology because it's just a bunch of single points, right? And if we're looking for holes in our structure, well, single points don't have any holes. It's just a whole bunch of connected components. So we need to start connecting the points in order to start seeing the structure. So if I have a point cloud like this one right here, as a human, I would look at that and say, oh, well, like it looks kind of like a ring, but of course it's just a bunch of points. If I start connecting points at low distance thresholds and I increase that distance threshold a little bit, I start to see, oh, there's the ring that I saw kind of as a human. And at some point, when I connect points that are far enough away, as I sweep up that distance threshold, that ring will be filled in. And the distance thresholds at which those structures, the rings and the voids, show up is the birth of that feature, and where they get filled in is the death of that feature. And so what you end up with when you do this thing called persistent homology to identify the birth and death thresholds of these features is a fingerprint of the topological structure of basically the point cloud. You know, if you would as a human look at it and say, oh, what's that shape? This is a fingerprint, a numerical fingerprint of what that shape is. And just briefly, we turned this notion of persistent homology on an arbitrary point cloud into an anomaly detector on CyberData, where we assume that behavior varies fairly smoothly from one set of time windows to the next time window. So when you have a bunch of these sort of log records from one, say, 10-minute time window, if you can summarize those with a high dimensional vector and collect a lot of those summaries, maybe from the prior day, you've got a whole bunch of these 10-minute windows summarized by a single behavior vector. If it's flow data, maybe you count the number of IP addresses, the number of ports, the total number of bytes, the average time length of the flows, those kinds of things. And you project these forward and you continue to get new 10-minute time windows and compare the point cloud of yesterday to the point cloud of yesterday plus a little bit of today and see how those point clouds are being perturbed topologically. You can identify when the behavior is shifting, when there's anomalies, and how big those anomalies might be. So if these blue points are your collection of baseline, and this red point is a new point, all the little blue points are from yesterday, and this new point is from today. How do I then can say that this point is, doesn't fit in to the rest of the points? It's probably more anomalous from the perspective of this persistent homology. So this is a tool that we have called Phantom, and we tried to apply this to the OptC data to identify a ping sweep. And what we did is we thought, well, let's first target our analysis to exactly the ping sweep. If we provide this sort of vectorization, right? I said for every 10-minute window, you have to vectorize your data by something. If we target our vectorization to exactly be the properties that we know the ping sweep to follow, we should be able to easily see the anomaly in that data. And unsurprisingly, that's what happened. If we did our vectorization with counting the number of process IDs, counting the different uses of port 0 and port 8, and the protocol of ICMP, we saw a large spike in the anomaly score right at the time of the ping sweep. If we start to relax some of our vectorization, not think of it directly targeting the ping sweep, what would a cyber defender do if they're just looking for any kind of anomaly? The more we relax the notion of our vectorization away from the known properties of the ping sweep, we still can kind of see the ping sweep, but we start to see other kinds of anomalies come through that can be targeted for a cyber defender to look into. Why was there an anomaly earlier, later? What is the kind of signature of the data? So the last thing, and I know I've got James, how many more minutes should I go?
Yeah, you can go a few more minutes. That's fine.
Okay.
We can leave like 4 or 5 minutes for questions. Should be enough.
Perfect. Okay. So the last thing that I want to get into is another notion of temporal. So this phantom that I mentioned is definitely a notion of sort of topology over time, but it's the topology of this point cloud over time. And another thing we can look at, pulling this back to the cyber hypergraphs, is how do those hypergraphs change structure over time? Not just how does this like feature vector point cloud change over time, but how does the structure of the behavioral interactions, how does that structure change over time, and can we identify anomalies in that? And so there's another tool that's related to persistent homology that's called zigzag persistence that looks at the sequence of simplicial complexes over time, not just as growing connecting point cloud vertices as they grow. So another paper that we have published this last year looks at applying this notion of zigzag persistence to temporal sequences of hypergraphs and identifying temporal anomalies in the behavior. And so I'll just briefly tell you about that. Here's a little bit of a inspiration or why we wanted to do this. If you look at just the hypergraphs of port versus image paths, this is an executable. The relationship between an executable using a port in benign data and malicious data, topologically, these two hypergraphs are the same. They're both two connected components. This one's a little bit bigger, but in the end, topologically, they're just two connected components. But if you look at the dynamics of how just the image path changes, let alone the hypergraph itself, but just the image path dynamics of the benign versus the malicious, there's a big difference. And so we thought, oh, let's look at the dynamics of how this structure changes and see if we can't use that as a detector. So temporal hypergraphs would be a hypergraph where every hyperedge has a time or a time interval associated to it. So here's an example of hypergraph names and time intervals that they're active. And if you walk through time, you can start to see a changing structure of the hypergraph. This might be a better illustration of that, where I have a hypergraph that has two connected components, this one big hyperedge. And now if I step through time, maybe this orange hyperedge becomes this larger purple hyperedge. So we've now gotten to one connected component. If the red hyperedge goes away, now I've got a loop, but now the green one went away, so I lose the loop, and now I lose the purple edge. The orange one is back, so now I'm back to two connected components. If I change from the hypergraph to the simplicial complex that sort of fills everything in, I can see how that changes over time. Oops, wrong direction. And in order to apply this notion called zigzag persistence, what we need to do is add the zigzags in. So we have to add in the unions of every pairwise hypergraph, and now we can start to track, much like in the persistent homology when we said, oh, a feature is born at a particular distance threshold and dies at another distance threshold. We can say here, oh, this component is born at the first threshold and dies at the second one because it's subsumed by the first component. This loop is born here at K2 and it dies at K3. It's lost. It's no longer. It's not that it's filled in. It's just no longer there. And so we can get a similar shape fingerprint in this zigzag context to say when different components and loops are present. And so I'll walk through and just mention that we applied this to the OPTC data. So we took log data, we created hypergraph snapshots from it. So for every IP address on every host, we created temporal snapshots of hypergraphs. we got a zigzag persistence barcode, and then we took that barcode and we took small sub-windows of that barcode, created a vectorization. So this is Adcock-Carlson coordinates are a simple way to get a numerical feature vector that can be used in machine learning, like an autoencoder, to summarize what's going on in that zigzag persistence. And then we looked at the reconstruction loss in that autoencoder to identify when the dynamics were off normal. And it turns out that this is just a single illustration of one IP address of the dynamics and the autoencoder loss for different activations and different, this is a variational autoencoder, to identify that the dynamics coming from the network in this IP address that we know was attacked from various ground truth analysis, and how the autoencoder identified that the dynamics was off at these various times, aligning with the ground truth. And not just for that one example, but also kind of across the board. If I look at the reconstruction loss for benign IPs at a given host, it's low. And if I look at the malicious IPs, it's much higher for reconstruction loss. And if I look at the training versus the test data, additionally, when there's not anomalies going on, the reconstruction losses are low. This column over here is looking at hypergraph summary statistics that are not derived from the zigzag barcode. And the zigzag barcode does a better job of picking out the anomalies than just the kind of hypernetwork science statistics. So the last, I'll just leave you with a few takeaways, that the sort of sea of CyberLog data is rich and allows for both real-time and forensic analysis by the defenders. But we can't just look for signatures of known behavior because the adversaries are constantly innovating. And hopefully I provided some insight into how mathematicians on my team are lending a hand to provide insight on this complex data for statistical anomaly detection, specifically using graphs and hypergraphs, topology, and mixed in a little bit of machine learning. This is not just my work. This is the work of a large team supported by the TDA for Cyber program. And that's all I have for you. There's a couple minutes for questions.
Yeah, thank you so much. That's fantastic. Really interesting stuff. Very practical level of anomaly detection, that kind of stuff. Do we have any questions? Oh, let's see. First, let me link there's the Qualtrics survey for all the student participants to fill out regarding the seminar. And with that, any questions? Got a couple minutes, can squeeze one or two in. People are still digesting the talk. I guess I'll go ahead and ask. Data sets can be kind of tricky to come by, like high quality data sets, especially when it comes to cybersecurity type data. I was just curious, the Los Alamos data set you showed, was that just a purely benign data set, or was there some malicious activity that was caught in that time frame?
Yeah, it's a good question. There is some malicious activity there. They have a red team data set. So the LANL data has authentication, flow, DNS, and something else I can't remember off the top of my head right now. But a small subset of the authentication data is labeled as red team.
Okay.
And the OpTC data has a lot of ground truth. It's annotated slightly differently. It's like a PDF basically showing a timeline. So you have to kind of go in and figure out what log events are malicious, but it still provides a reasonable way to analyze that data.
Okay, cool. It looks like someone linked the data set. So this is publicly available? That's cool.
Yeah, both LANL and OpTC are publicly available.
Okay, awesome. Yeah, thanks for the link. Well, can still sneak in a question. Well, if anyone has one. Otherwise, it's 4 o'clock, so I'm not seeing any last minute questions. 3, 2, 1. Oh, There's one. What aspects of lower level or high school mathematics do you find to be the most important or valuable to aid students in the ability to move into this field of college study?
Oh,
Yes.
good question. Um, so I think one that could be really important is like statistics, and that would be lower level, high school, college statistics could be really helpful. Practically, I would say computing, Python coding or other kinds of software, um, dealing with cyber data sets is a challenge, and it's one thing to come up with some algorithms. It's another thing to be able to try and test them on real data. So having that ability to develop some of that yourself is very helpful. Yeah, I think those are the two that I would say on the lower level.
All right. Cool. One last question before we call an end to the seminar for today. In the next 3 years, where's your area of research going to focus?
Great question. So one thing that we've seen is that some of these hypergraph structures tend to correlate with adversary activity in cases. But those patterns, if you just look at the pattern, it might show up as benign as well. One example is maybe remote desktop. A remote desktop session versus an adversary connecting to a computer, those could look very different or very similar as structural patterns. And so we need to layer on top some more of the metadata. And so I think one of the places that we'll be going in the next few years is marrying some of these structural analyses with machine learning and NLP and metadata analyses to kind of fuse those two pieces together.
All right, great. Yeah. Well, thanks once again. And thanks everyone for sticking around a couple minutes extra to hear the questions. So with that, yeah, have a great rest of your days.
Right.
Bye.
Thanks all.